Let me start. So, as Dennis mentioned, we will introduce a new immersion tin electrolyte today, which is called Stannatech 2100. Brief outline, I will start with a brief introduction on immersion tin in general, and we'll then go through some of the properties of the process, so of the properties of the layer, soldering performance. We will also talk briefly about typical defects in immersion tin plating and the respective root causes, and we'll then, let's say, go through the highlights of this process compared to the existing immersion tin solution that we have. I will also take the chance to introduce some of the post-treatment solutions after immersion tin that we offer, which kind of, let's say, accomplish the performance of the process, and we'll end with a brief summary and takeaway, and then followed, of course, by the Q&A session. So let's start with the introduction. A few words about immersion tin in general, which probably most of you know. Nevertheless, let me just to get everybody on the same page. Immersion tin plating is a displacement reaction, so we dissolve copper during the deposition of the tin and create the tin layer on the copper directly. Means when the immersion tin layer is assembled, we form a copper tin IMC where the tin layer is completely dissolved into the solder. And immersion tin layers are typically used for soldering applications or press fit applications. There are a couple of benefits which makes immersion tin attractive for the PCB market, which is it's a very robust finish, so it has a long shelf life of 12 months minimum. For soldering applications, it does not contain any nickel, so it's a good solution for high frequency applications. It's very corrosion resistant compared to other finishes, which makes it very, let's say, attractive also for automotive applications. And it's relatively low cost compared, for example, to any PIG or the finishes which contain precious metals. So there are some limitations which needs to be considered during the or for the immersion tin process. There is a certain risk for whisker growth, which is kind of process imminent. Whiskers typically grow caused by the formation of the intermetallics during the aging of the immersion tin layer, this formation of the intermetallics then cause stress, and this may lead to whisker growth. So there needs to be approaches to prevent whisker formation for immersion tin layers. For sure, we don't have any barrier layer here, so there is a certain copper diffusion through the tin layer, which in the end limits to a certain extent also the shelf life of the finish. And the immersion tin layer or the immersion tin process is a very aggressive process, so it's highly acidic, and therefore there is, let's say, at least a certain risk that it attacks the solder mask, and in particular if solder resists are not properly applied or are not well cured, then there might be an interaction between immersion tin and the solder mask which is not beneficial and which leads to defects of the final finish afterwards. We will come to this later on as well. Another, let's say, risk is that we create a high ionic contamination. It's somehow also related to the solder mask compatibility, because again, if the solder mask is purely applied, if it's not well cured, it may, let's say, soak in the immersion tin chemistry, and this will later on create high ionic contamination values. But we will talk on this later on as well. Brief, let's say, key summary of the benefits of the Stannatech 2100. There are, as mentioned, certain risks for the existing immersion tin processes, which are somehow connected to the very high viscosity that immersion tin plating solutions have. The high viscosity has actually two, let's say, causing two limitations. You have a poor or worse solution exchange, so you need to really take care, also equipment-wise, to bring fresh surface to the fresh solution to the surface, and in particular in narrow features, the solution exchange might be poor, leading then to excessive copper dissolution in the edges, causing this corrosion, which is unwanted. Another effect, which is sometimes seen, is that you have a dark appearance after reflow, and this is related to a failure, which I will also explain later on, but it's also related to the, let's say, poor rinsability of the chemistry and the high viscosity. So the approach for the Stannatech 2000 was really to reduce the viscosity of the solution by having a different formulation, and by getting this lower viscosity, having a better solution exchange in small features, and also a better rinsability of the tin chemistry in the process, so that this prevents or helps to prevent these typical defects which can be observed with immersion tin. One key information which might be also important is our immersion tin process comes along with auxiliary equipments like the constanic and the crystallizer, which helps to extend the bath life of the immersion tin, so that you don't need to run the bath in feed and bleed, but can run the bath with constant performance with the same plating solution. And the new formulation is also compatible with the auxiliary equipment, so it can be just replaced as a drop-in in existing lines. In terms of process flow, it can be applied in vertical as well as in horizontal mode. Actually, let's say from the micro etch step on, the process is comparable. We have a conditioner, a cold conditioner step similar to our Stannatech 2000, and then followed by the active immersion tin plating step, and then followed by post-treatment, which is a post-immersion tin step, a diluted immersion tin pass to reduce the drag-out losses of the process, followed then by active rinse concepts, which can be either alkaline thiourea rinse or the so-called special rinse, which I will also introduce later, followed by different post-treatment solutions, which are actually optional and can be applied to further improve or reduce the risk for any appearance issues of the immersion tin layer. The only difference we have in the acid cleaning step here, so we typically apply a different cleaner in horizontal than we do in the vertical process. Let's look to the layer properties, starting with the thickness distribution. And what you see here is a comparison of a reference process with the Stannatech 2100, and we look to the thickness distribution depending on pet sizes. So this was measured on a test substrate with different pets with different pet sizes, and also having connected and isolated pets here in a pet size range of 0.2 square millimeter up to 49 square millimeter. And what you see on the right is actually that the target thickness is pretty similar, and also the thickness distribution is in a similar range for both. Let's go to the soldering performance. So what we usually do when we check our processes is that we do different kinds of soldering tests, soldering to check the solder wettability of the immersion tin layer, which are on one hand side solder tests where solder paste is printed and then the solder spread capability is measured, or also doing tests like solder floatate, tests where liquid solder is applied to the final finish and the wetting is measured. These tests were all done with different aging conditions, so in as received after IPC reflow and after thermal and humid aging. Let me go to some of the tests, starting with the solder spread test. I think this is a solder test which is well known. What is done here is that a solder depot is printed on the pad, and then the panel is reflowed in the reflow oven. And what we finally measure is the spreading angle of the liquid solder spread on the surface. And we are comparing here the immersion tin with the reference tin with the Stannatech 2100 for different aging conditions in as received after thermal aging and after thermal aging plus reflow in this case. And what you need to recognize, of course, a lower spreading angle would indicate a better solder spreading here, means lower values are the ones preferred that we would like to see, and the higher the worse wetting we get. And the acceptance criteria for immersion tin layers are to be have an angle below 20 degrees for as received conditions and below 25 degrees for aged conditions. So what we can see in the graph is that we can achieve the minimum requirements for all conditions, and that we even for the Stannatech 2100 see slightly better results compared to the reference process. So we have slightly lower angles for sure. All of them are passed. Let's move to the next solder wetting test. So in this case, again, solder is printed on pads. These are rectangular pads in here. I hope it can be seen that we print the solder in, let's say, 2 triangle shapes. And what is observed is after the reflowing, so after the heat treatment, is how good the solder wets and connects, and how far the liquid solder connects on these pads. So in this case, it means we have a better solder wetting the higher the value gets. So again, we compare against our reference, and again we see that we have the best values for as received conditions. After the aging, we have slightly decrease of the wettability. Nevertheless, also here we see that the Stannatech 2100 layers appear slightly better than the reference values, and for sure all the solder wetting results are passed. The third test, which we usually do, is a de-wetting test. So what we do in this case, we have rectangular pads on our test panels of a size of like 1 centimeter times 1 centimeter, and here we print 4 solder depots, the square solder depots on, and then the samples are reflowed. And what you see here are different, let's say, performance of wetting, and we actually distinguish 6 grades of wettability. The first 3 would be all passed. The 4, 5, 6 would be all failed. And what we look at is for the grade 1, for example, would be excellent solder wetting, means the solder is liquid and connects completely, and the pad is completely covered with the solder. For the grade 2, we have still good connections sometimes, but some, let's say, in some of the areas, the printed areas remain as they are. In the grade 3, we have the solder stays where it is, it gets liquid, stays where it is, does not connect, but it does not de-wet. And so all indications for de-wetting are starting from grade 4 upwards. There we really see that we have areas where the solder removes from the pad edges, and this is what we definitely do not want to see. So that would be all fail. And we compare again the reference versus the Stannatech 2100, and we see that we have, for the most cases, a solder degree of 1, 2, and 3, but nothing or no failed conditions, so no 4, 5, or 6 is observed, neither for the reference process nor for the Stannatech 2100. Also here, actually, we see a bit more of the grade 1, so again, slightly better than the reference process. And finally, the solder gap test. This is another wetting test where we apply solder on a different test structure. What we do here is we have rectangular long lines, pad lines, and these lines are printed with solder depots. We apply the reflow aging, and then we measure how long the solder depots, let's say, manage to connect. And again, here we have the higher the value, the better the solderability is, or the solder wetting is. And you see again that we have a very comparable conditions for the immersion tin reference and the Stannatech 2100. And they are all again passing the target requirements. So these were all like solder printing tests where we print the solder depot, do the reflow, and then check the wettability. Another approach is to have liquid solder and, let's say, splash the liquid solder to the panel and check the wetting of the solder on the pads and PTHs. So this is the selective wave soldering test. Also here we have test structures on our test boards where we have PTHs with different diameters and also pads with different pad sizes, which are then, let's say, immersed or exposed to the liquid solder. And what we evaluate here is then if we see any, let's say, PTHs not fully filled with solder, and that all the rectangular or the rings are fully covered with solder. And also here we don't see any difference between the Stannatech 2100 and the Stannatech 2000, so performs well. Nevertheless, there are issues or there are risks that soldering for immersion tin has limitations and that we may see defects. And what I would like to talk a bit here is what are the reasons for this. For this, let's look on what happens during the assembly with the immersion tin layer during the reflowing of an immersion tin layer. When we have an as-received layer right after the process, we have the immersion tin layer on the copper, as you can see here in the FIB image. We have already a very fine, very thin formation of an intermetallic phase, of a copper 6 tin 5 phase, and then on top of here's the protection layer. So we try to have a kind of graph here to show what we see. After the first reflow, the IMC is formed, so the copper 6 tin 5 IMC grows and reaches, let's say, 80% of the overall tin layer. Also, what happens is the tin oxide layer here on top increases slightly in thickness, and when the layer then sees a second reflow without being assembled, what happens is the copper 6 tin 5 IMC further grows and reaches basically the tin oxide layer, so the top of the overall tin layer thickness. Tin oxide layer also slightly grows further, and we have only minor free tin remaining in kind of islands here between the IMC grains. So this needs to be kept in mind when talking about immersion tin layers aging during the assembly process. As mentioned, also the tin oxide layer grows during the assembly process. These are actually values which were published in a PhD thesis from Bosch a couple of years ago, where tin oxide was measured in S received, and then after aging, after reflow aging, and it was compared reflow aging under nitrogen and under air. And what you can also see that when you have the reflow process under air, that then a stronger oxide layer is formed on top of the layer. So this is actually the condition that we have when the tin layer is aged. What kind of soldering defects we can typically see when we look on immersion tin? So there is, for example, so-called self-dewetting, which is an uneven appearance of the immersion tin layer after the assembly or after the soldering, the reflow aging. And what you see is that the tin layer appears dark and uneven, that you have these bulbs here on top of the layer and this inhomogeneity. A second failure can be dewetting. Means the solder did wet the surface first, but then removed from the edges and dewetted, and finally non-wetting, meaning really the layer did not wet at all and the solder remains in corners or certain areas and does not fully wet the surface. What can be reasons for that? For the non-wetting, it's really caused by kind of physical barrier between the surface and the solder, which prevents the solder from wetting. Dewetting is, yes, caused by the solder first wets the surface, but then is removed. And we'll talk about the root causes for this later. And finally, the self-dewetting actually appears when the oxide layer is damaged, and during the assembly or during the reflow process, the liquid solder underneath, or the liquid tin underneath the oxide layer, cracks through the oxide layer, comes to the surface, and then hardens there, causing these kind of pearls here on the surface. And actually, for all the three types of soldering, the root causes can be nailed down to being residues on copper and or contaminations on the tin surface, or even volatiles from the solder mask evaporating in the reflow oven and then recondensating on the tin surface. A bit more looking into what's going on there. For example, if you have any residues on copper which are not removed before the tin plating process, so they right after the tin plating, they are here somewhere sitting at the interface between the tin and the copper. And then what's happening during the first reflow cycle is that they can move with the IMC growth into the tin layer and may even affect the formation of the IMC growth, or may even trigger the IMC growth in these areas. We did a test to, let's say, check the impact of contaminations on copper on the IMC growth, and that was actually a pretty simple, but I think pretty, let's say, obvious result. What you see here is test coupons. On the top, clean coupons which were properly cleaned before the immersion tin plating, and on the bottom there are coupons where a fingerprint was applied on the coupon, and then the immersion tin was plated on top. And then the immersion tin was removed by stripping. And what you see here in the pictures are the conditions after different times of stripping. So we are stepwise stripping the tin layer off. to see when we can reach the copper. And on the top, where we had the clean copper, we can see that we really strip off the tin evenly, and we don't see any residues, and we have a clean copper. On the bottom here, where we had the fingerprint, we can see that apparently here IMC has been formed, which is removed more slowly by the stripping solution, or which is more difficult to be dissolved by the stripping solution, so that we see that here, where we had the fingerprint, IMC has been formed stronger than apparently on the clean surface. So what is the meaning? It means that where we have contaminations, different IMC, stronger IMC is formed compared to a clean surface. And this for sure can then have an impact in the secondary flow cycle, because then the IMC grows further. And if we have contaminations here, these may, let's say, attack or destroy the tin oxide layer, and in these areas the liquid tin here, the remaining liquid tin, comes through the top and then forms these inhomogeneities and dark areas on the surface. So this is something which we would like to prevent. We did some further studies to also try to correlate the defect areas with organic contaminations, and that worked well with investigating defect panels with a UV fluorescence microscopy, because there we were able to visualize the organic contaminants which are UV active, which otherwise cannot be detected with bare eye or with microscopy. And what we could really see is that in the areas which appear dark and apparently show some self-de-wetting, high concentrations or high active values of UV fluorescence could be observed. So it was possible to correlate the organic contaminants to these defect dark areas of the immersion tin. Beside that, what was also tested, for example, was to see the effect of the solder resist on the de-wetting defects in immersion tin. For example, we did tests with different cured solder masks, so having different curing conditions with solder masks, and then checking if we can improve the performance of the immersion tin layer. And we also try to analyze the, let's say, the leach out of the solder mask if the solder mask is not properly cured. And this could be done actually by analytical measures to compare different curing conditions of solder mask, and we actually could identify some, let's call it markers, which represent or which can be detected as leach out components from solder resists if they are not properly cured. And what you can see here in this graph is an HPLC TOF-SIMS analysis of a solder mask leach out after different curing conditions. So you see the reference lines in black, and then we have applied different UV bumps or UV cycles to cure the solder mask. And what you can see is that you can reduce the leach out of the marker components by applying UV bumping. So meaning there is a chance to improve the solder mask properties or conditions, or to make the solder mask more resistant towards the immersion tin process by additional UV treatment. And this brings me actually to the, let's say, brief summary on what can cause soldering defects in immersion tin. They in the very many of the cases, they can be traced back to really contaminations, either residues on copper which are not properly removed before the immersion tin process, which can be even residues from the solder mask process. For example, if there was a not fresh developer anymore, then there is organic remaining on the copper, which maybe not properly removed in the pre-treatment process. It can be caused to residues on the tin, means the rinsing after the tin is not properly, so it's important to really have a proper rinsing after the tin process to really get rid of all the chemistry, the tin plating chemistry of the pads and the panels. And it can be finally also volatiles from the solder mask in the reflow process, which evaporate and then recondensate. So for here, it's really important to have a proper solder mask controlled process and a fully cured solder mask. And all these measures actually can help to prevent soldering defects. Why do I tell you all this? Because when we go back to this one of the key key needs is to have a appropriate rinsing and to really get rid of all residues from the plating chemistry. And this is something which is very difficult with the existing tin processes because they are highly viscous, and therefore the one approach for the Stannatech 2100 was to reduce viscosity to get a better rinsability. And we could actually by this new formulation or reduce the viscosity by half compared to the existing Stannatech 2000 process. And this improvement of the reduction of the viscosity actually helps in two ways. In one way, it improves the exchange of the immersion tin solution during the plating in narrow areas to prevent, as mentioned in the beginning, these excessive corrosion in really narrow regions in blind microwires or any undercuts, to reduce the risk or to have a better exchange and a better, let's say, providing fresh tin solution and to don't have this mismatch of excessive copper dissolution in areas where no tin can be provided. Another benefit is a better rinsability. So it's easier to get rid of the chemistry. And what you see in this graph here is what has been done. This is the conductivity measured in the rinse after the immersion tin process, after certain times when the panel from the tin process was immersed to the rinse. And what we see is that for the Stannatech 2000, which acts here as a reference, is a higher conductivity can be measured or can be observed compared to the 2100, meaning we drag in more of the plating chemistry into the rinse, meaning also that we have that we need more rinse water to get rid of the chemistry, that we need more activity in the rinse to get rid of the chemistry compared to the 2100. So 2100 is, due to the lower viscosity, easier to rinse off and brings less drag out into the rinse, so it also helps to reduce rinse water consumption. And finally, it's also related to the attack to the solder masks. So we are comparing here the reference process with the Stannatech 2100 and see that we have a lower undercut to the solder mask. I don't want to make you afraid. So this solder mask was applied with a very weak conditions to really exaggerate the attack of the immersion tin process. So it's not the standard what we see on on every panel, but this was really just to compare and to make this attack visible. And what we still see is that due to the better exchange, the undercut for the 2100 is lower. And finally, this is also something which we can observe on icy substrate panels, that this is here comparison on the plate on the C4 side of a BG of the icy substrate. And what we see with the reference process is that we have undercuts here under the solder mask of up to 10 micron actually in some areas. Here it's also pretty strong, and we even see some copper corrosion here in these gaps where we have a poor solution exchange, and this can be also significantly being improved. We still see an undercut with the 2100, but it's let's say reduced by half. So we have an undercut of 4 to 5 micron versus really 10 micron in these areas. So it's reduced a lot, and we also don't see or don't observe this copper corrosion in these undercut areas. So it is also caused by the better solution exchange during the process. And finally, I think it's not only about chemistry, but it's also about the equipment. You are aware we are also offering the horizontal systems for the immersion tin plating. So just would like to mention that it's not just a flush bar for the rinsing and also for the immersion tin plating process, but there is a lot of engineering know-how also behind for the fluid delivery devices in the plating module as well as in the rinses, to ensure that we have best, let's say, agitation and really bringing the chemistry and the water right there where it is needed. And there are, let's say, different systems, approaches, which really ensure to have the best solution exchange and really rinsing conditions to clean the panels after the plating process. Finally, a few words about whiskers. There are certain standards which needs to be fulfilled. So we have, for the Stannatech 2000, we have already implemented the so-called anti-whisker additive, and which is added to the plating solution to prevent whisker formation in the plated immersion tin area. And what was done here was to check different concentrations of the anti-whisker additive, which is actually also applied in the Stannatech 2100, so it's the same approach, and then to check the whisker formation after aging of 1000, 2000 and 3000 hours in higher humidity. And this is now just showing the results for the 2000 versus 2100 in S-received conditions. There we don't see any whiskers. So we in particular check this in PTHs, where you typically see them easy and first. And then we did comparisons with without the anti-whisker additive and with adding with anti-whisker additive, and there we see that without, we see some whisker formation in the PTHs. With the additive, the surface is defect-free, so there are no whiskers detected. Similar for the after 2000 hours aging. Again, here we see some whiskers formed with a 0, but as soon as we have additive inside, there are no whiskers being formed, and similar actually for the 3000 hours aging. And finally, that brings me to the post-treatment solutions that I would briefly like to introduce, starting actually with the rinsing. We talked a lot about rinsing because rinsing is really one of the key steps in the whole immersion tin process, simply because of the viscosity of the tin solution. And there are different rinsing concepts already in place. What we now recently introduced is a so-called Stannatech special rinse. So this is an additive which is added to the rinse after the immersion tin process, and the target for this edit or this rinse is actually to prevent copper redeposition and also to reduce the rinse water consumption. It works by using thiourea, which is also known already from thiourea rinsing, and but with the additive, it's possible to significantly reduce the thiourea consumption in the rinsing and also to reduce the rinse water consumption. This can be actually applied in vertical and horizontal, and it's actually implemented directly in the drag-out rinse module. And it's a drop-in for existing lines, and it also helps to prevent discoloration defects on the immersion tin pad after the rinsing and drying. Another post-treatment I would like to show is the Ionics 2100. It's also a new solution, and let's say the purpose of the Ionics is actually to reduce ionic contamination, which is, let's say, or where the demands became more strict in the recent years, let's say targeted by the automotive requirements. And which are the ionic contamination is strongly connected also to, again, to solder mask. Sorry to say that, but we see that there are different strong variances depending on the solder mask type which is applied. Nevertheless, there is a chance to reduce ionic contamination also by additional post treatments. And what you can see here in the graph on the right is, for example, two different solder mask types in green and in blue, and you see already there is a big difference between those two when there is no ionics applied, but if you apply ionics, you can actually reduce it even further, and for both types of solder masks. So it helps to reduce ionic contamination values. It's also a drop-in, and yeah, it's a new post-treatment for the tin. Another post-treatment solution is the tin post-dip 8. This one is actually to prevent yellowish discoloration of the immersion tin layer, which may also happen after the reflow aging. And it's actually an inorganic kind of additive, which is, let's say, applied on the tin surface and which is actually removed and in the soldering process. It does not impact the soldering performance of the tin layer and can also apply directly in the existing processes. And finally, the tin post-dip 2020. This goes actually in a similar direction to like the Stannatech 2100, targeting the oxide layer here. If you remember all the explanations that I tried to explain the reasons or the root causes for the solder dewetting, for the self-dewetting defects here, we need to have a strong tin oxide layer, and that is actually what the tin post-dip 2020 helps to provide. It strengthens the oxide layer, and by that helps to reduce the risk for dewetting or self-dewetting defects, for appearance defects. Simple test that we did here was just to immerse the tin plated panel in the tin post-dip solution, then do the reflow aging, and what we see afterwards is that in the areas where we applied the post-treatment, we have a nice white clean tin layer, while on the areas which were exposed to air and were not immersed to the tin post-dip 2020, we have a dark appearance. So this is really a clear indication that the increase of the oxide layer can help to prevent these defects. This tin post-dip can be combined with all the other post-treatments. There is no interaction of these in between, and they also, all of them, they don't have any negative impact on the solderability of the surface. Briefly, customer references. this is actually our reference base for the Stannatech 2000. We have a worldwide spread, and it's installed in more than 120 lines at the customers. More of 20 of them are dedicated for SE substrate, and we are just starting now to, let's say, convert customers to the 2100 and to qualify the new process for the customers to change. Okay, wrapping up briefly, Stannatech 2100 key benefits are the reduced viscosity, improved rinsability, better solution exchange, and also a reduced solder mask attack, which all helps to reduce the let's say typical issues that we know from immersion tin plating. And yes, just not to forget to mention, it's compatible with the auxiliary equipment, of course, also with the horizontal equipment that we have, but also with the auxiliary equipment, keeping the benefits provided by that we have a long lifetime, that we have a very constant plating conditions in the process, that we don't need to have a feed and bleed, so a reduced chemistry consumption compared to feed and bleed plating. And yes, that's it. So thank you for your attention, for joining the webinar, and yeah, done.
Thank you, Britta. Let's continue with the Q&A session. It was a pleasure to follow your presentation. So we received many questions, and I would like to remind you that we will cover as many as possible during this session. And all of the rest will be answered by Britta after the webinar via email. So let's start with the first question. Considering increasing interest from automotive OEMs, is there any benefit of this chemistry compared to the existing process?
There is an I think we've in the recent year, 1-2 years, we got increasing requests from automotive OEMs, in particular in regards to surface tension. And there we actually see that we have benefits with this process as well, because it forms a different crystal structure, or slightly different crystal structures compared to the Stannatech 2000. So we have a slightly rougher crystal structure compared to 2000. It comes along with a slightly different appearance as well, but in the end it really helps to have to fulfill the demands for the surface tension from automotive OEMs. So we can now achieve let me think about that. We can achieve, I think they require 40 millinewton per meter, and we can achieve now more than 75. So we are at least far above the limits where we actually struggle sometimes with the 2000. So that was quite at the edge, and with the 2100 we are far above now.
Okay, thank you. Let's continue with the next question. Do we need to have a full new chemistry makeup, or it's just a new version? Is it 100% new chemistry, or just
Yes.
Modified or upgraded version? So this is a bit broader question.
It's a good question. It's actually, let's say we have when you know the Stannatech 2000 process, we have actually one key makeup solution, and then we have a couple of additives and replenishment solution, which are also continuously replenished during the process. Let's say all these replenishment solutions, they stay the same. The key makeup solution is different because really the formulation, the key component, or let's say some of the main components are different. You cannot make up the bars with the existing Stannatech 2000 chemistries completely, but you have to replace one makeup solution. The rest stays the same.
Thank you, Britta. Also, it was mentioned that due to the lower viscosity, the wetting issues can be improved. What is the mechanism behind?
Is actually there are two. One is for sure that the rinsing is improved, so it's easier to get rid of the sticky tin chemistry, and the second is really that we have a better, let's say, yeah, replacement or exchange in the plating already. But the key for the dewetting issues is really the better rinsing, that you get rid of any residue chemistry from the plating process when you go to the rinsers, and that you don't have any remaining chemistry which could then affect the assembly process.
Thank you, Britta. Let's continue with the next one. Can this chemistry achieve the thickness higher than 3 micrometers?
Oh yeah, I mean it's an immersion tin process still, so therefore the thickness is somehow limited. If you take the time, it's possible. We do, or we have an immersion process, for example, that we applied for QFN as well, and where we can achieve the 3 micron, but it really takes a long time, and for sure it will also, how do you say, it's a replacement reaction, so you also will dissolve a lot of copper. There is in development also an autocatalytic process, so depending on what is finally the target application where you think of, maybe you can reach out to me later by mail as well, then we can discuss. We have an autocatalytic tin process also in development, which we target in particular now for micro LED applications, where also high tin plating is required or considered as a kind of solder depot, so that might be an alternative. The immersion tin plating has certain limitations. I wouldn't say it's the let's say it's not the intention for the process. Actually, it was developed to target thickness of 1 to 1.1 micron as a standard thickness for standard PCB applications.
Thank you, Britta. Let's continue with the next one. You highlighted the compatibility with Stannatech and crystallizer. Can you describe a bit more? What does it mean?
So we have two auxiliary equipments, Stannatech and crystallizer, and the purpose or the task of them is for the crystallizer. The crystallizer is actually to remove the tin or the copper. The copper sludge which is formed during the plating. Of course, when you plate, it's an immersion process. You increase the copper content, and the idea of the crystallizer is to remove the copper so that you can run the bars with continuous copper concentration, and which helps to, or that which enables you that you are able to run without feed and bleed. For the Stannatech, the purpose is different. In particular, when in horizontal, when you run the process in horizontal, you bring a lot of air into the process by the high agitation, and therefore tin 4 is formed. So you actually have tin 2 plus in the solution, and then it's oxidized to tin 4, and the tin 4 cannot deposit on the tin. So the Stannatech, or the purpose of the Stannatech, is actually to reduce the tin 4 ions back to tin 2, so that you also can have a constant concentration of tin 2 in the process. And finally, these are the key benefits of these auxiliary equipments, that you have a constant concentrations of copper and tin 2 in the plating solution, and no variations, so that you have always really the same concentrations and constant conditions during the plating. And yeah, and that prevents you also from running the process and feed and bleed, meaning you have less chemical consumption, you can save costs, and you can run the process for a long time without having any new makeup. That's a key benefits. And yeah.
Thank you, Britta. And let's have the last question of today's session. Can this chemistry run without post-treatment?
It can. The post treatments are all optional. It really depends on the requirements that you have. For sure, it can, but there are, depending also on the OEM demands, what they look for, there might be a request for super wide appearance after assembly, then the post-step 8 might be applicable if there is a demand for low ionic contamination. As I mentioned here, also the solder masks have a big impact, so might be necessary that if you run a certain solder mask, you need additional post-treatment to really remove the ionic contamination, which would otherwise be too high. So they are somehow optional. They just, let's say, improve the final finish